so let's begin. A little bit about me. My name is Alon Wolf. I started learning C++ in high school because I wanted to make video games and found out I really enjoy it. Back then, all I knew about C++ was that there was a pop-up I need to click on whenever I install a game. Today, I'm working as a senior software engineer at Medtronic, specializing in computer graphics. Where I work, we make robots for spine surgeries, so I get to do what I love, while also help to improve patients' lives. And in my spare time, I like to experiment and try new things in C++. And I also participate in game jams. In this talk, we are going to take a deep dive into the world of compile-time parsers, but we will also cover many other aspects of the language, so I hope you will find it useful, even if compile-time parsing isn't your cup of tea. So, about the structure of this talk. First, we are going to talk about what it means to write expressive code and how we can write more expressive code in C++. Then, we are going to look at open source compile-time libraries. For each library, we will look at its API, design, and some implementation details. Finally, we will see how we can use compile-time parsers and integrate them reflections, and also shows how they can be used to create functions, types, and tree data structures. So what is a parser? For our purpose, a parser is something that takes text or tokens and returns some value or a parsing error. So for example, in the compiler, the source code is converted first into tokens by the Lexi, and then the parser takes the tokens and uses them to create a syntax tree. Or in a web browser, we can pass text directly to a JSON parser to create a JavaScript object. One popular way to create parsers is with parser combinators. So a parser combinator allows us to create a new parser by combining existing one. So for example, if we have a parsing function called parseString that takes the input text and the current parsing position and returns a string or an arrow, and we have a similar function called parseInt that returns an integer or an arrow, we can create a new function that will parse a string or an int by first calling parseString, and if it fails, calling parseInt. Because all these functions have the exact same arguments, we can simplify this pseudo-syntax and remove the function arguments. Another way to create parsers is with parser generators. So a parser generator can generate a parser from a grammar definition. Some popular parsing algorithms that are used in parser generators include LL1, LR1, LALR, and many others. Here you can see example of a grammar definition that uses the EBNF syntax. And in the example here in the last line, you can see that assignment is defined as identifier, followed by colon equal, followed by either a number or an identifier or a string. Okay, now let's look how we can make our C++ code more expressive. So when we write software, we usually have some idea in our head. It can be about an algorithm or some business logic or a data transformation. And we use the programming language to represent this idea and communicate it. When we communicate it, we first communicate it with the compiler, which will need to compile it into the binary, and also with other people that work with the same code base. So, and this is usually also includes ourselves in the future. Here you can see an example of, and the expressiveness of the language is defined by the range of ideas that it can represent. So the more ideas you can represent with the language, the more expressive it is. And here you can see part of the definition from Wikipedia, and while it does describe the term, I don't think it emphasizes enough why we should care about it. So here is a different quote. Always code as if the guy who ends up maintaining your code will be a violent psychopath who knows where you live. I think it pretty much says why we need to care about expressive code, but in other words, without expressive code, you can end up with an unmaintainable mess of a code base. As I mentioned before, we use the programming language to communicate the idea. So when we say expressive code, we mean code that communicates its purpose, which means what it does, how it should be used, or why it was written. And it relies on two things: the syntax of the programming language and the naming conventions. In this talk, we are going to focus more on the syntax part. As the language evolves, we get new syntax that we can use to write more expressive code. So here you can see two examples that initialize a vector with 4 integers. But the C++11 example is more expressive because it has less boilerplate. It doesn't need to create a static array or use size of, both of which burdens the people who work with this code. Another feature that we can use to write more expressive code is with operator overloading. So by using operator overloading, we can use operators to call a costume function for specific type. So in this example, by overloading the division operator, the code can be written from left to right and without parentheses. Also, the division operator is a good choice for this use case because it is a common way to represent paths in many operating systems. So, domain-specific language, or a DSL, is a language that is designed to solve problems in that specific domain. So first we need to know about the domain and about the syntax of the DSL, but once we understand it, we can use it to more easily solve problems in that specific domain. So here we have some examples of domain-specific language, which include SQL, CSS, regular expressions, and makes that we use to rack make files. While SQL is great for writing database queries, we wouldn't want to use it to represent our build system. Here you can see an example of a DSL in C++. So we can create a DSL in C++ by using multiple operator overloading. What you see here is part of an XML parser implementation that uses the Boost Spirit library. And Boost Spirit is a library for writing runtime parsers, and it has a DSL. So in the first line, we define text as all characters that aren't opening angle brackets. Then we define starting tag, end tag, and finally XML is defined as a starting tag, followed by a list of node, followed by a matching end tag. As you can see, we can make C++ look like a completely different language. But there are still limitations. So the syntax still must be valid C++ syntax because it needs to be parsed and compiled by the C++ compiler. So if we take a look at a small part of the code from the previous slide, we can see that the syntax for parsing a list of node is star node, and it is implemented by overloading the star operator, also the pointer dereference operator. Okay, let's assume we want a different syntax for our DSL. What if we wanted to write node star instead? Well, in this case, we will get a compilation error because the unary star operator must be on the left side of the expression. Let's do a quick recap of everything so far with a filter transform example. So here we have a vector of cats, and when we want to get the names and IDs of all the cats over the age of 42. So we iterate over the input vector, check if the age is over 42, and if it is, then we place back a tuple with the name and ID. One way we can make this code more expressive is by using modern C++ syntax and replace the iterators with a range-based for loop, which communicates better that we are iterating over the entire vector. But this is 2024 and we have ranges now. We can use the overloaded pipe operator to chain multiple operations and pass the output of the previous operation to the next one. So here we first filter all the cats based on the age, then we transform each cat into a tuple of name and ID, and finally we collect them all into a vector. With this, our code literally says filter transform. But what if we wanted to write it in a different way? What if we wanted to express it by using SQL syntax? Well, we can do it with a parser. So first we create the parser, then we parse the syntax into a function. Finally, we call the function, and we are done, right? Well, not exactly, because there are some differences. We have the runtime overhead of creating the parser and also parsing the string into a function. Also, the return type of the function must be type erased, for example, by using std_any. This is because it depends on the output of the parser, which happens at runtime. So at compile time, we don't know what type we get. We can solve all three problems by shifting the parsing into compile time. Now we no longer have the runtime overhead of creating the parser and parsing the string into a function. And we also know at compile time the exact return type. Finally, we can use a string literal operator to parse to encapsulate the parsing logic, and now our filter transform code is just a single line of SQL syntax. So let's generalize what we just saw. In the previous example, we used a compile time parser to convert a string literal of SQL syntax into a callable object. But the general power of compile time parsers is that we can use a string literal to create an island of our own costume syntax inside the C++ code base and convert it into any compile time value. So is something like this even possible? The answer is yes, and by the end of this talk you will know how. But we need to start from the beginning, which in my case was a Google search. So I asked Google, hey, did anyone try to do this crazy thing in C++? And the answer was yes, of course, there is already a Boost library for it. I mean, in hindsight, I should have expected it, and this leads us to the first library of this talk. Boost MetaParse is a compile-time parsing library by Abel Sinkovich. Everything in this library uses C++98 except for the creation of the compile-time string. So in C++98, we have to write each character as a separate template parameter. And these kinds of bits are goal of achieving expressive code. But in C++11, we can use the boost metaparse string macro with a string literal. This is how a typical parser in boost metaparse looks like. And it uses template structs, which are also known as meta functions. So here we have an outer struct with an inner apply meta function, where the apply meta function takes the input string and the current parsing position and returns the parsing result along with some additional information. You can think of the outer struct like a class and the inner apply meta function as a method of the class. So let's talk about the syntax of meta functions. The syntax and technique needed are pretty horrendous, and this is not me saying, it's from the C++ core guidelines about template meta programming. While you might say that pretty horrendous is a bit harsh, having to express everything in terms of template structs instead of if branches, for loops, and other basic syntax elements is definitely not something that we would like to do. Here you can see part of a calculator parser that uses boost metaparse with template structs and judge the syntax for yourself. Let's go over some features of boost metaparse. So we can use it to compile time parse some string into either a runtime function or compile time function. The difference between them is whether we are returning a struct that contains a apply meta function, or if we return a struct that overloads the call operator. We can also use boost metaparse to create meta functions with Haskell-like syntax, which you might prefer over the regular template meta programming syntax. So in this example, the meta underscore age ace is a compile time map, and it acts like a symbol table. So the import call adds a new meta function to the map. The define call creates a new meta function from a Haskell-like syntax and adds it to the map. Each call returns the new modified map, so we can nicely change them together. And in the end, we can get the new meta functions from the map to use in C++. These techniques enable importing and exporting meta functions between the Haskell parsing environment and the C++ environment. We can also use boost metaparse to create a parser from a grammar definition. Each grammar rule contains the syntax that it needs to parse and an optional semantic action to take. Okay, so as we said before, the boost metaparse string is a macro that we can use to create a compile time string from a string literal. Here we will see how it works, but what I want you to take from this is not the entire implementation and the inner working, but more to see how difficult it was to create a compile time string in C++11. So the macro expands to something like this: a call to make string with the length of a string, then followed by many calls to str8 with the string literal and the running index. str8 is a concept function that takes a string and an index and either returns the character at that index or 0 if the index is past the length of the string. In C++11, concepts per function were limited to just a single return statement. So this is pretty much the limit of what was possible. And after we evaluate the concept per function, we can see that the parameters to the make string function are the length of the string, followed by the characters of the string, and then a lot of trailing zeros. So, make string recursively concatenates the characters until it reaches the original length of the string, and then we get the compile time string that we wanted. Look how much tricks and effort were necessary to create a compile time string, something that we can easily write today in just a few lines. So, and with this we are going to do a time skip and move to C++17, and also every time we will change subject or move to a different library, I will have some image or a comic like this one might explain why we don't have time machines. So Lexi is a compile time parsing library by Jonathan Mueller that uses C++17. It has a DSL for writing parser combinators, similar to the DSL that we saw with Boost Spirit. And it also supports Unicode strings and can parse at runtime and compile time. We can create a parser in Lexi by defining a struct that has a rule and a value. The rule specifies how to match the input string, and it can be implemented as a parser combinator. And the value specifies how to construct the parsing result. As you can see in C++17, concept became a lot more powerful. Now, so the rule is defined by an immediately invoked concept per lambda, and inside the body of the lambda we can do a lot more than just a single return statement. Lexi also has an online playground where you can write your parser, you can write your input string and see how they matches. It is very interactive, it is powered by Compiler Explorer, so it has the experience that we all know and love, and it is a great tool for learning about Lexi and parser combinators in general. Now let's talk about performance. Lexi can parse at both runtime and compile time. And here you can see the result of JSON parsing benchmark. And as you can see, Lexi is on par with other popular JSON parsing libraries. So you get a library that can parse at compile time and runtime without sacrificing performance. Now let's look at the implementation of a typical parser inside of Lexi. So here we have an outer struct with a context per parse function, similar to the apply meta function in Boost meta parse. But this time there is some difference between the implementation. Now we have a template struct between the outer struct and the context per function that takes a next parser template parameter. The reason that it is here is because the parse function can then invoke the next parser with additional or modified parameters. You can think of it as a callback or continuation. And this solves the problem of dealing with different return type. The parsing results are simply passed into the next parser as function arguments. So a sequence parser combinator is a parser combinator that takes two parsers, P1 and P2, and creates a new parser where P1 must be followed by P2. And in Lexi, it is implemented as simply an alias that redirects the next parser template parameter. So in this case, during parsing, P1 will invoke P2, which will then invoke the next parser. Anyone know what this syntax is or what it does? Yes?
Is it an email address, regex?
Oh my God, yeah, you know it. Yeah, so this is an RFC 822 email address. I didn't expect it. Yeah, email address validation regex, and it is used in some Perl module. And this leads us to the next library, which is about compile time regular expressions. So CTRE was created by Hanna Dusikova, and we can use the library to create regular expressions and use many operations with them, like matching, searching, and capturing, either at compile time or at runtime. It uses, and it also supports Unicode strings. So to create a regex, we can either use the CTRE string literal operator and provide it the regex pattern, or we can pass it as a non-type template parameter to the match function or any other one. Yeah, we can also specify the names inside the regex pattern to then extract the captured values. And one limitation of the library is that the regex pattern must be a compile time string, so it must be known at compile time. But it is already a common practice to have the regex as part of the source code, for example, if you want to match a date pattern. So in terms of performance, the constructions of the regex objects from the pattern happens at compile time. So it has zero runtime overhead. Now, matching and other operations can be done at runtime and compile time, and as you can see from this benchmark result, CTRE is much faster than stud regex and have similar performance to boost regex. Okay, so the compile time string is passed by using this fixed string class, which has a constexpr constructor that takes a fixed size array and then copies it and store it inside of a data member. Then we can, if we look at the implementation of the CTRE literal operator, we can see that it takes a fixed string as a non-type template parameter. So when we call the literal operator with a string literal, the string literal will be passed to the constexpr constructor that we saw in the previous slide to create the fixed string, which will then be parsed to create the regex object. The parsing of the regex object is done by using LL1 parser. And here is a quick overview of how it looks. So the LL1 parsing algorithm takes the input text, and inside of it, it has a stack that it pushes and pops values from. And it also has a parsing table that represents the rules of the grammar and is used to determine which action the algorithm should take next. So the stack is implemented as an empty struct, in this case a type list, and pushing and popping and performing other operation of the stack is done with function overloads. The parsing table is also implemented as just empty structs and function overloads. So here you can see, like, the rule, it provides a lot of overloads for the rule, which is essentially performs a lookup. I think this is a very elegant design decision that shows how such a complex system can be implemented with these two basic building blocks. Then, during parsing, this is the parsing loop of the LL1 algorithm, and it is greatly simplified. But first, we call the overloaded rule function to determine which action the algorithm should take next. And then it can either return an error or the successful result, or modify the parameters and recurse to the next iteration of the loop. Okay, so we've seen the LL1 algorithm, and our next challenge, we will face the LR1 algorithm. And this leads us to the next library, which is ctpg, or compile time parser generator. And as the name suggests, we can use it to generate an LR1 parser from a grammar definition at compile time. It uses C++17, and you can use this library with your own Lexer or let it generate one for you. So in order to generate the grammar, we first have to define the grammar rules. So here we define a non-terminal that represents an expression, and then terminals for the minus operator, multiplication, and a number. With ctpg, we can define operator precedence, so that multiplication will be evaluated before subtraction, and also associativity. So if we have a chain of subtractions, they will be evaluated from left to right. We can also define a non-terminal with a regex pattern, like you see with the number here. Okay, then we take all the terminals and non-terminals and combine them into the grammar rules, and this can be done with an expressive DSL. And because we have already defined all the non-terminals, we can use them to create recursive rules. I cannot possibly cover the LR1 algorithm in a single slide, but we will look at some implementation detail inside the ctpg library. So here is a quick overview of how it works. It first takes the grammar and uses it to compute item sets, where each item set represents a state that can be reached during parsing. Then it computes all the transitions and parsing table that will be used to do the transitions between the states during parsing. Here you can see an image of what the item sets and transitions look like. And in many runtime implementations, they are implemented by using a set or a map. But we don't have a context per set or map. I mean, we are still in C++17. So how it was done? First, let's look at how a single item in the LR1 item set look like. So here we have the index of the rule that it belongs to, the current parsing position inside the rule, and the terminal of the next look ahead that can follow it. This is the one in the LR1 algorithm. It has one look ahead. Then ctpg computes the maximum value of each one of the data members that we saw. So here we have the number of rules, the maximum number of parsing positions, and the number of terminals. Then it multiplies them all together to compute the address space of all possible LR1 items. And so an item set is implemented as just a bit set over the entire address space. Then it defines two functions to convert back and forth between an index and an item set. And so that adding, removing, and finding items is implemented with basic bit set operations. It shows that some compile time some compile time problems can become a lot simpler if we can find an upper limit and use a fixed size container. Okay, we are about to move to C++23, and we are about to look at some more libraries, and this is a hint for what the next library is about. Can anyone guess? I mean, this one I expected. The email one was the one I thought will be hard. Yeah, so this is a macro photo of a crab, and we are about to look at libraries that implements Rust macros in C++, and the reason is because the logo for Rust is a crab. So, macro rules was created by Maxim Pasichnik. It uses C++23, and we can use this library to create a DSL with the Rust's macro rule syntax. It is more of an experimental proof of concept than a full library. Before we will look at the library, we need to know what Rust's macros are. So here is a quick overview. Rust has two types of macros. Procedural macros and declarative macro. A procedural macro or a proc macro in Rust is a compile time function that takes an input string and generates an input and just takes a token stream and generates a token stream of the new generated code. It can be invoked directly by using exclamation mark and then some tokens, or it can be passed to another macro. So in this example, the derive macro takes a bunch of procedural macros, and then it will invoke each one of the macros with the tokens of the struct below it. The library that we are about to look at is not about procedural macros, but at this point you might have an idea about how they can be implemented in C++. So declarative macros use the macro rules style syntax, which has two parts. The first part specifies how to match some syntax pattern, and the other produces an AST of the new generated code. So in this example, the vec macro will match a list of expressions separated by comma, and it will generate a code that creates a temporary vector and generate a push call for each one of the expressions. Let's see how we can do something similar in C++ by using the macro rules library. So here we define a struct that inherits from a macro rules matching syntax. So in this case, it is the word sum followed by a list of numbers. And this struct has a constable transform function that takes the context and will use to produce the output.
Sorry, what does the $sign mean here?
The $sign is part of the macro rules syntax. So here you can see the dollar is used to match, to say that there are like, it's like declaring a variable that will be used inside the tree. Yeah, so in this case, it will be a list of numbers. Okay. So inside the transform function, we can extract the arguments from the context and use toDepply to expand them into an argument pack. And then by using a fold expression, we can calculate the sum of all the arguments and return it. When we want to invoke or apply a macro rule, we can call apply rules with the name of the rule and the text that we want to match. So internally, macro rules uses a compile time parser to convert the matching syntax into a template instantiation that represents the syntax tree. You can also write this template directly, but I find the macro rule syntax easier to work with and more expressive. If we take a look at a part of the AST, we can see that it has an identifier. So, and in fact, for macro rules, when we have an identifier inside the syntax in macro rules, it is only used in two ways, either for lookup or equality comparison. So the library calculates a 32-bit hash value of this string identifier because it is easier and more efficient to pass around a single 32-bit hash value than a variable size string. And then, so when we call apply rules, it passes the name of the rule, and it also converts the text into a string literal by using a preprocessor macro. Something to keep in mind if you are using a preprocessor macro to convert text into a string literal. The first thing is that if you have comments, they won't be included as part of the string literal, so you get support for comments for free. Other thing is that syntax highlighting will keep working on the text, at least in all the editors that I tested. And if you have multiple white spaces, they will be collapsed into a single space. So keep that in mind if you are considering a syntax that relies on white space, like in Python. Now we are about to move to the final compile time parsing library of this talk. And this is one that I wrote, and we will use it to implement some examples. So, YACP, or yet another compile time parser, is a very basic parser combinator library. It has a DSL similar to the ones that we saw with Lexi and Boost Spirit. It doesn't do anything fancy like the indirect, the next parser indirection. Instead, it returns everything as fixed size container. And it uses C++23. So because we're about to implement some parsers with a parser combinator, let's go over the syntax. So we can use the binary OR operator to create a choice parser. So in this case, it will either parse an integer, and if it fails, it will try to parse a double. And this one returns a variant. In this case, it's a variant of int or a double. The bit shift right operator creates a sequence parser. So in this case, we have an int that must be followed by a comma and then must be followed by a double. And it will return a tuple, which in this case is a tuple of an int and a double. The star operator will create a list parser, so it will try to match the same parser again and again until it will fail. And this one returns a fixed capacity vector. And the bit shift right equal will take the successful parsing result in terms the parser succeeds and forwards it to a lambda. You can think of it like the bind operator in Haskell. Do you have a question?
Yeah, so wait, where do you get the 16 from if it's allowed to be parsed like indefinitely repeated after each other?
It's hard-coded in this case, like, yeah.
So it could be anything?
No, this one you have to know like what capacity you are going to use beforehand,
Okay.
and not pass it. Yeah, I said it's a very basic library. It's not like
So
everything is
in
fixed size.
In the first line, like you can have a maximum of 16 ints followed by commas, right?
Yeah, if you have 17, then you will get a compilation error.
And you just have to know that beforehand, right?
Yeah.
Okay, okay, cool.
Why? So in the previous slides you used variant and tuple, but there on this next one you're using a fixed vector. Why not a stud array or?
So there is a different stud array. You know like the capacity of the array, but you know how much of it you used. So the idea is that you can think of it like a fixed vector, a vector with fixed capacity. So you can have up to 16, but if you have less, then you have like, so stud array at compile time only has like the size of the array with.
That's the maximum size.
Yeah, this is the maximum size. It's not the size used. So in this case,
Okay.
it will only like for this one, the size, like the capacity will be 16, but the size will be 3 because we only have 3 integers. So in C++23, we can use stud expected to represent the parsing result, which can be some value or a parsing error. And a parser is just a wrapper around a stateless lambda that takes the parsing context and will return a parse result. Where a parsing context is a struct that contains the input string and the current parsing position. We can use a concept to create a concept that checks if a type is an instantiation of the parser template by trying to construct a parser from the concept argument and checking if they have the same type. It is a useful trick to create a concept that checks if a type is instantiation of a certain template, but it will only work if in case it has a copy constructor. So we said that the bit shift right operator creates a sequence parser, but we want to have a different implementation depending on if the user wants to create a new sequence from existing parser or take a parser and append it to an existing sequence. And we can do it with concepts. So the sequence parser concept first checks if the type satisfies the parser concept, and then checks if it has the sequence parsing function. Because it takes the parser concept and adds another condition on top of it, it is more specialized, and therefore, when we call the bit shift right operator, it will reach the correct overload, and we will not get ambiguity error. Now I have a question. What kind of string is used in every C++ application and must always be known at compile time?
Literal string. Literal C string.
No.
Empty string?
No. So the answer is it's the source code, because it's the input to the compiler, so it must be known at compile time. I mean, if you think about it, the source code is nothing more than just another compile time string. And because we know that compile time parsers work great at consuming and producing compile time values, it has a lot of potential when we integrate it with reflection to either take the reflection data or to generate the reflection metadata. Do you have any questions up until now? Okay, here is a quick overview of the current state of reflection in C++. So right now, C++ only has compile time introspection. Having reflection of part of the language is still far away. Hopefully we will get it in C++26. But for now, here are some reflection libraries that you can use. An approach that many of the reflection libraries take is to use a preprocessor macro to generate the reflection metadata. So, for example, by using the RCPP library, you can use the reflect macro to reflect all the members of a class if you write it inside of it, or you can also write it outside of a class to reflect just the public ones. So we can also use a compile time parser to generate this reflection metadata. Here we have a macro that takes some text and uses it twice. The first usage is it takes the text and pastes it as it is so that it will be compiled. In the second usage, it converts the text into a string literal and pass it into a compile time parser. So if we will call the generated getAttributes function, then we'll get the result of passing the string literal of the source code into the attributes parser, and with this way we can reflect the attributes of a struct. Let's generalize it and extend it so we can reflect multiple properties of the code. So here we have two macros. Both of them generate a function that uses a compile time parser to reflect some information from the string literal of the code. One for the attributes and another for the members. Then we can create another macro, which we will call define, that takes a list of macros and some text, and it will first paste the text as it is, and then it will convert it into a string literal and use it to invoke each one of the macros. This is one way to implement Rust's derive macros and create a similar system to procedural macros in C++. Okay, let's continue with reflection. So we just saw how we can use compile time parsers to generate the reflection metadata, but a more interesting use case is to use the reflection metadata to add more capabilities to our compile time parsers. So first we will add this resolve identifier function, and for the sake of fitting all the code into slide, the word identifier was shortened to just ident. And what it does is it maps a compile time string into some value. So in this case, it maps the X string literal into a pointer to a data member. It uses a function overloads as a lookup table, similar to what we saw in CTRE, and it also converts the string literals into 32-bit hash values, like we saw in macro rules. Then we can use a repeating macro to generate a resolve identifier for each one of the data members of the struct. And then we can have a function to get a member by an identifier. So first we take the type and we call the static resolve identifier with the identifier to get a pointer to the data member. And then we can use the pointer to data member with the object to get the actual data member. Now with this, let's add it to a compile time parser, and our target syntax will be a list of identifiers separated by dot, and we will use it to create a function that returns a nested data member. I know this is not the most exciting syntax, but it is a starting point that we will build upon later. So our parser will match a list of identifiers separated by dots, and it will return a fixed capacity vector of 32-bit hash values of each of the identifiers of the nested data members. An approach that I sometimes use when I write compile time code is to first write the logic as runtime-like pseudocode and then convert it to compile time. So if we want to get the member, we first initialize a result vector which will point to the input vector. Then we iterate over the list of nested data members and call getMember and store it to the result to get the next data member. And finally, we return the result, which is what we want. In order to make this code work, the first step that we need to take is take all the compile time arguments and move them to be template parameters. In this case, the member was moved from a function argument into a non-type template parameter.
You go back and forth.
Yeah. So members was here in the function arguments list.
Yeah.
And when we go, it becomes a template, a non-type template parameter. Okay. The next step that we need to take is replace all the loops with either recursion or a fold expression. In this case, we can do it by using a recursive lambda to iterate over all the members. And with C++23, we can easily write recursive lambda by using deducing this. So the this autoref self is a reference to the same lambda that we are in, and when we invoke it, we perform the recursion. Okay, the last step that we need to take is replace all the branches with if const expr. In this case, we only have one branch that checks if we need to exit the recursive lambda. Then we can wrap it in a string literal operator, so that takes a fixed string similar to what we saw in CTRE. And then it returns a lambda that first it will use the compile time parser to get the fixed capacity vector of members, and then we'll call the get nested to get the nested data member of the argument. Okay, now let's look at Compiler Explorer and see what assembly it generated. Okay. Yeah, so here we have two functions that return a nested data member. One that uses the regular C++ syntax and another that uses a compile time parser. Now, if you look here, you can see that the compiler has generated a lot of code. Let's first look at what isn't here. Nothing that is related to the compile time string or the parsing is here. Everything that is here is related to the implementation of the get nested function, and most of it is related to the recursive lambda. The reason that the compiler generated so much code is because we compiled it with O0, which essentially means the compiler emits the code as it is without performing any optimization. Now let's change it to O of 1. Yeah, it's generated the exact same assembly for the regular syntax and the compile time parser implementation. So we have a zero runtime overhead abstraction. Again. Wait, something here is not. Okay, yeah, sorry. So let's extend this syntax and add two new operators. The colon operator will perform a range-based for loop, and the pipe operator will take the current value and use it to call a function. So we need to create the new parser. So the pipe operator will match a pipe followed by an identifier, and it will return a pipe struct, which is just a wrapper around the identifier. The iterate operator will match a colon, and it will return an empty struct. Then we can create our new parser by combining them all. So here we have a list of parsers where each one can either be a pipe or an iterator or a list of nested data members. Then inside the implementation function, we have a similar implementation that uses a recursive lambda to iterate over all the variants. And first we check what we need to do. So if the variant is a list of data members, then we call the get nested function that we implemented to get the nested data member. If we need to iterate, we perform a range-based for loop. And finally, if we need to, get a pipe operator, then we extract the identifier of the functions that we want to call. And now what? I mean, we need some way to call a function based on an identifier. We can do it by using the same resolve identifier trick, but with a global function instead of just a static member function. So in this case, the resolve identifier will map the square string literal into the square function. And now we can just call resolve identifier with the identifier to get the function. Well, actually no, because we might have issues if the square function is defined in a different space, for example, inside of a namespace. So when we call the resolve identifier, it will not find the function. We can solve this issue by moving the resolve identifier call outside of where we implement the functions that the parser returns into where we use the syntax. So in this case, where instead of calling the resolve identifier, we call this scope lambda with the identifier, and the scope lambda called the resolve identifier. Because the scope lambda is defined where we use the syntax and not where we implement, it will find the correct lookup and return the square function. Okay, finally, we can just wrap it inside a macro that we will call scope. Because our scope lookup is just a lambda, we can also use it to reflect local variables. So here, this one, if you will pass it an identifier of string literal x, you will get a reference to the x local variable. Okay, let's compare the syntax. So our new syntax can be written from left to right, and the overhead of writing an entire range-based for loop is reduced into a single character. Also, we can chain multiple function calls with the pipe operator. So overall, we have achieved a very expressive syntax for this very specific kind of problems. And let's look at the generated assembly. One second. Yeah, so here we have again two functions, one that uses the compile time parser and another that uses the regular C++ syntax. And let me see. Well, it's kind of hard to see if I match them correctly from here, but they produce the exact same assembly. So even with the more extended syntax, we still have 0 runtime overhead. Okay, does anyone know if this code compiles? Oh, well, the answer is it doesn't compile. Can anyone know why it doesn't compile? Yeah. So the reason it doesn't compile is because if you will try to run it, you will get an error that C is not a valid type for template non-type parameter. And the reason that it is not valid type is because it is not structural, and this is because it has a private data member. So in C++20, the definition of a structural type was modified to include context per variables of a class type. And the two requirements of a class type to be structural is either if it first have to have all base classes and all non-static data members be public and non-mutable. So all the direct data members have to be public. Also, the types of all the base classes and non-static data members must themselves be structural. So this is a recursive definition that all the entire composition tree must be public. Now, I said that we passed a fixed vector capacity of variants and tuples, but if we will try to do it, it won't work. So if we will try to pass a tuple, a stud tuple, it will not work because stud tuple has private data members. One way to get around it is with a lambda. So we can create a lambda that returns the tuple, pass it as a non-type template parameter, and then call it inside to get the tuple. But another way, which is what I did, was implement a basic version of stud tuple and stud variant where all the data members are public. it took less effort and code that I expected, thanks to deducing this. So we have seen how we can use a compile time parser to create functions. Now let's see how we can use them to create types. And the syntax that we will want to match is TypeScript-like syntax that you see here. So here we have an opening curly brackets followed by a list of members where each member is an identifier, colon, and another identifier. And then finally a closing angle curly brackets. And our parser will return a list of tuples where each tuple contains two values, one which is the identifier of the name and another is the identifier of the type. We can use the same resolve identifier to get a type based on an identifier, and this one is done by using the helper type wrapper class, which enables us to return a type as a value. Okay, so before we implement the entire struct, let's start with a single data member. So here we have a template struct that takes the identifier and type wrapper of the type of the data member. First, it creates a data member of that type, and it also defines a function that to get that data member based on the identifier. Once we have a single data member, we can make more of them, and we will need to combine them all into a single struct. And we can do it by this combined struct, which takes a list of template parameters and inherits from all of them. Then inside the implementation, here we have the functions that we'll use to create a struct from the string literal. So first we parse the string to get the list of all the data members. We create an index sequence for the length for how many data members we have, and expand it into a parameter pack. Then for each data member, we use it to create the struct member type, where the first parameter is just the identifier, so we extract it from the tuple and pass it. And the second one is the type wrapper of the type, and we can do it by calling the scope lambda with the identifier to convert it from an identifier to a type wrapper. And these are all created, passed into the combined members so that we combine them all inside a single type. And then we can just return a type wrapper of the new struct type that we created. And here you can see an example of how the new syntax looks like. And the struct macro takes the text, converts it into compile time string, and use it to call the create struct function. Okay, so we have seen how we can create types, and we've seen how we can create function, but all of our syntaxes so far were linear. Now let's look. It is very common to want to parse trees. So the next, we will create a tree data structure, and our target syntax will be JSON. So here we have, we define array, member, object, and a string. They will all use fixed capacity containers. And we have a variant of all the possible data types of the variant. Notice here that object, array, and string inside the variant are pointers. So usually, if we want to create a JSON in runtime, we can do something like this, and we have, and it is also common. Generally, if you have three data structures, then you usually have a pointer from the parent to its child nodes. So in this case, ideally, you can use new and store them inside a smart pointer. But if we'll try to make it a const-expr, then we will get an error. You can use new and delete inside a const-expr function in C++20, but you cannot store the result in a const-expr variables. They must all be deallocated. So we can solve this issue by using a compile time allocator instead. So here we have a basic compile time allocator, which takes a list of types, and it contains a tuple of fixed vector for each one of the types. When we call the add function, it simply stores a value inside one of the types and returns a reference to it. And so we can just replace the calls to new with a call to our compile time allocator.add. And now we can create the JSON. So this is a struct that will represent our JSON, and it holds our compile time allocator and a var that will point to the root of the JSON tree. Inside the constructor, we pass the JSON, we pass the input string and the allocator, and we store the result as the root. And here is a syntax how it looks like to create a context per JSON. Now, one thing you might worry about is, well, you just have a compile time allocator. How will it affect the binary size? I mean, this object can be very big. So if it is only used at compile time, it will not be included as part of the binary. If it is also used in runtime, then it must be included. And in this case, there are some options that you can take to reduce its size. One of them is to first pass a more lightweight parser just to calculate the necessary capacity, and then use it to decide how much to allocate. The other one is to first allocate it with a vector with a very big capacity, and then copy it into another context per variable, which will only allocate the capacity that is needed, and use this one in runtime. Okay, now something about using compile time parsers. When should you do it? So ask yourself, do you need a domain-specific language or a general-purpose language? Compile time parsers right now are best suited for domain-specific language, and if you need a general-purpose language, well, you already have one. It's C++. Can your desired syntax be expressed with C++ operator? If it is, use operator overloading. The last thing to keep in mind is how will it interact with C++. So if you have a self-contained syntax like a regex or einsam, these are the best. You have no interactions. You don't need to worry about it. If you do need to interact, then you have some options. One of them is to have explicit access, kind of like we saw with the Haskell parsing environment in Boost MetaParse, so you can explicitly import and export. Another option is the scope-based lookup with the resolve identifier mechanism. This one requires reflection, but you may already have reflection if you somehow got access to the future, or if you are using some reflection library, for example, to do serialization or create binding from a scripting language. Which compile time library should you choose? If you are using any version before C++17, your only option is Boost MetaParse. For C++17 and above, it depends on what you want to do. So if you prefer to write your parsers with parser combinator, use Lexi. If you prefer to create them from an LR1 parser generator, use ctpg, and for regular expression, use ctre. If you want to try more experimental things with C++20, you can check out macro rules to see how we can have macro rules syntax to create a DSL, or YACP to see how they can be integrated with reflection, and also the full implementation of the examples that we saw here. Let's talk about compile time errors. So here we see two compile time errors. One is the ones that I like to get, the other one not so much. The first one is because I forgot a semicolon, and it is one that GCC generated. The other one is because I provided invalid syntax to ctre. You can understand a little bit from the error, so you can see that it failed because the syntax is incorrect, and it failed at parsing position 4. So we do have enough information to understand the problem, but this is not the kind of error message that we get. And like this is just the end of the error message. You know how template error messages look like. So Emery Berger has a talk where he speaks about AI for development tools, and he passed the compile time error from ctre to CY, which is a tool that helps diagnose and fix compilation error. And the tool was able to give a perfect explanation and suggest a solution. So if you're facing compile time issues, you should give it a try. There are some ways to print a string at compile time. Vittorio used it and talked about it in his blog post to implement compile time wordle, and I use it to create compile time code generation libraries. Here you can see below a code of what it looks like, the compile time printing. And for more information, you can check the links here. Okay, compiling. Now we are going to talk about compile time, how long the compile time will take, or how many solve fights you can expect to make in the same days that you are writing the compile time parser. So first of all, the compile time depends on a lot of things. The complexity of the syntax that you want to parse, which parsing algorithm you are using and how well optimized it is, the compilers that you are using, the options that you are using, the hardware, and many other options. So the best thing is to benchmark it and profile it for your own use case. But I still did some benchmarks which might give you a rough idea of what kind of numbers you can expect. So I compiled the same, all the examples that we just saw, the project, one with the entire project and another with all the compile time code removed. The results that you see here are the average of 5 runs. And I didn't include the variance because it was very small. The difference between them with the compile time included or not is about 1.5 seconds. Then I created a different benchmark where I parsed 1,000 structs. First one was using like regular C++ structs, and the other is struct that uses the TypeScript-like syntax with the compile time parsers that we saw. So the regular C++ syntax adds around 100 to 200 milliseconds over the baseline. And it's good to know that the compilers are very well optimized for this task. And the compile time parser implementation overall adds around 14 milliseconds over the baseline, which averages to around 40 seconds over the baseline, which averages to around 14 milliseconds per struct. So one recommendation is you should write compile time code as similar as you can to runtime code. It makes it a lot more easier to understand, and it makes it a lot more easier to debug. So if you need to debug it, you just remove the const expr and start putting breakpoints. The same code can also then be used in runtime, and it can lead to a faster compile times and less memory usage. So I had a different JSON implementation that parses the JSON into a template tree. And this one took over 1 minute and 4 gigabytes to compile instead of 1.5 seconds. Yeah, so I have encountered the same issue when having like a large template instantiation with other compilers, so I recommend avoiding it whenever possible. So we've seen the progress of compile time parsers from arguably C++ 98 up to C++ 23. It's not something new, and they have evolved very much. Their usage and how well they operate depends on the difficulty on writing and using compile time code, and also on compilation speed. We can assume that all of these things will continue to improve through new language features, discovery of new techniques, compiler improvements, and faster hardware. So in C++ 23, we also have the if const eval keywords, which enables us to detect if we are running at compile time or at runtime. And this one can be used to further optimize a function to the execution environment. In C++ 26, there is a proposal, which as far as I know has been accepted, that enables us to generate a static assert message at compile time. And we can use it to create much better error messages for the compile time parsers. So one way to do it is, so if we have the parser, we can then take the parsing result, check it if it fails, and then pass the error messages. Because we can generate the error message itself at compile time, we can make it descriptive and look like how we want it to look instead of what the compiler does. And also we can put the static assert at the most top level we can. This way it will not print like, if we have the static assert very deep, then we will have all of the template instantiation stuck. With this we can remove it and just have the error and format it however we want. So there is a reflection for proposal for C++26. The code that you see here is based on the current state of the proposal, which might change or depending on what happens with the proposal. And so this is how you would use it to implement the get member based on an identifier. So we can use the caret operator to reflect the type and get all its non-static data members and iterate over them. Then for each member, we can check if the name is the name that we want to find. And then we can use this colon brackets operator to dereflect it, so convert it from the metadata object into the actual data member to get the data member from the object. Also, we can use the template for to have compile time context per iteration instead of using recursive lambda or a parameter pack expansion. I couldn't find the description of the template for inside the reflection proposal, so this one might be related to a different proposal. Yeah?
How are you comparing the fixed string name for equality with the result of std meta name of?
It has a conversion to a string view.
Okay.
Yeah. Okay, another thing we saw that we can use compile time parsers to create the struct type, but we didn't actually create a brand new type. We were just creating a new template instantiation. With the C++26 proposal, you can actually create an entirely new struct by using the synstruct function. So here we create a vector of metadata informations about the new struct members. Then we iterate and push a new NSDM, stand for non-static data member. So we push a description of a non-static data member that contains the type of the data member and the name of the data member. And then we pass this new vector to the synstruct to generate the meta information of the new struct that we want to make. And finally, we can create a new struct by calling the make struct function with the syntax of the struct that we want to make. It will be parsed and it will return us the meta information, which we can then use the colon brackets operator to convert into the type and store it in an alias. So in recent years, there were a lot of rise in successor language. They are all languages with their own syntax that aims to have a significant improvement in some areas over C++. But one problem that they all face is how to integrate it with existing C++ code. So if we zoom in at one slide, and this one is from Herb Sutter's recent talk about CPP2, we can see that he asked, what could we do if we had a clearly demarcated bubble of new C++ code via an alternative syntax for C++? So what I see here is bubble of new code, different syntax in C++. Now, are you thinking what I'm thinking? Yeah, so I marked it C++20 ? Because I'm not sure if it's possible right now or viable, but I do think that we will eventually reach the point where you will be able to write something like this. So you can just write your CPP2 code or whatever you want, and use a compile time parser to convert it and then use it, and you have seamless integration and interoperability with C++. Okay, now these are all syntaxes that we can already parse or at least partially parse. And if we keep projecting it into the future, we can assume that the gap between what we can do at runtime and compile time will continue to decrease. So right now at runtime we can parse pretty much any language that we want, and if we assume that gradually it will be possible at compile time, then we will be able to parse any language that we want at compile time. So you can potentially parse and evaluate JavaScript at compile time. I don't know any reason why you would want to do it, but I think it will be possible. And we said in the beginning, we said that the power of a language is based off the range of ideas that it can express. So what if we had a language that can express all other language, or at least wide variety of them? But maybe I'm completely wrong and we will all be replaced by AI. I mean, who knows? It's the future. Yeah. So finally, before we finish, here is an image from the talk by Abel Sinkovich in CppNow 2012. So the same conference 12 years ago, where he presented about Boost Meta Parse. And I think like my personal hope is that in hopefully less than 12 years, there will be another talk about compile time parsers, and it will show some of the examples that we saw here today that uses C++ 17 and 23, and say, look how much difficult and how much effort was needed to do something that we can easily write today. All right, thank you very much. I think how much time do we have left?
15 minutes.
10 minutes.
Yeah, so I have bonus slides. I wasn't sure how much time we have left. So, yeah, so if you want to know how the derive macro is implemented, so when we call the derive macro, we pass it, it's the first argument is the list of macros that we want to reflect. And then we have like the type and the text. So the derive macro will first output the text as it is. Then it takes the type and the arguments and pass them as a single parameter to the for each macro. And the next arguments to the for each macro is the call macro and eval of the macros. So what eval does is it removes the parentheses. So the macros will be passed as each one their own argument. What the call macro does is simply paste the macro and the args after it, so that the macro will be called with the same args. Now, the for each macro is implemented like this. First we need to count how many arguments we have. So here we have the count args sample and the count args. So if we call count args with, let's assume we have 0 arguments, then the VA args will be nothing, and then it will call it with 3, 2, 1, and 0. So _3 will be 3, _2 will be 2, _1 will be 1, and the n will be 0, which is the 0 arguments that we passed. If we passed 1 argument, everything will be pushed by 1 argument, and so n will be 1, and if we push 2, n will be 2. Here I have it up to 3, but potentially you can extend it to whatever limit you want. And so when we call the for each macro, it concatenates the for each underscore with the count of arguments. So we can have like either for each underscore 3 or for each underscore 2. And each one of them evaluates one arguments from the pack and then passes the rest to the next one. So 3 will evaluate, so for example, here in the example that we saw, we have 2 macros. So it will get 2 for each macros 2s, which will then perform the action, which will reflect the attributes, and then pass the next one to for each macro 1, which will then evaluate and create a function to generate the data members. Okay, thank you. Yeah, this is the rest of it.